Video 2 from Newton's law of gravitation. Let's answer those questions. So what's the relationship between the masses and the force of attraction? Well, the force of attraction is directly proportional to m1 multiplied by m2. Okay, second one, the relationship between the distance and the force of attraction. It's an inverse square law. So the force of attraction is inversely proportional to r squared, where r is distance, or the force of attraction is inversely proportional to the distance squared, or the force of attraction is proportional to 1 over r squared. The g value is the gravitational constant. You'll find that in the log tables. Okay, we have mass, so why don't we feel a force of attraction towards everyone? We do, it's just so small, it's difficult to notice it. Also, you might feel there might be a force of attraction towards other people, but there are so many of them that they may cancel each other out. That's another way of looking at it, because they're in all directions. The force of attraction between you and the planet is much larger than the force of attraction between you and other smaller, less massive bodies. But also, we experience a force of friction which will prevent you moving. And that really comes into the last one as well. So the last one is the force will cause an acceleration, typically, but we don't accelerate because of the force of friction preventing us from doing so. Okay, let's look at using the formula with a slightly different question. So the force of attraction between the Earth and the Sun, we're looking for now in this case. And we're given the mass of the Earth, given the mass of the Sun, and given the distance between them as well. So the same idea, formula, substitution, and answer. And if you look at this value, it's 3.52 by 10 to the 22 newtons. That's huge in comparison to the previous calculation. So the force of attraction between the Sun and the Earth is substantial. And what that does is it keeps the Sun and the Earth connected, essentially. It keeps the Earth going around the Sun. Without that, it would almost be like in that little cartoon diagram there. If that force stopped existing, it would be like the hands of the Sun and the hands of the Earth disconnected, and the Earth would just fly off in a straight line. So that force is responsible for making the Earth travel around the Sun in a circular motion. Now, the other thing to remember here is that the force of attraction is experienced by both the Sun and the Earth. So let's have a look at the effect that has. So, part 2, what is the acceleration of the Earth and of the Sun caused by this force? So the Earth will apply F is equal to ma. I've put the force of attraction and the mass in there, and the acceleration is 0.0059. It seems quite small, but have a look at what happens with the Sun. The Sun is much, much smaller. So while the forces of attraction are the same, because the Sun is more massive, it's more difficult to make it move. The Earth is easier to move, so the Earth will actually experience, I suppose, a reasonable acceleration, if you can call that a reasonable acceleration, when compared with the Sun anyway. So both experience a force towards each other, both experience an acceleration, but because the Earth is less massive, its acceleration is going to be much larger. And that acceleration keeps the Earth going around the Sun. Okay, let's go back to the questions at the start. So, when you fall out of the plane, do you fall and the Earth remains at rest, or do both the Earth and you remain or travel towards each other? And it is the second one. Both you and the Earth experience a force. That force causes both of you to move, but because you're much, much, much less massive than the Earth, you experience more movement than the Earth will ever experience. In fact, the force of attraction that the Earth experiences is almost negligible. And question number 2. What's with the acceleration? Again, the answer is B. So we know that the force of attraction varies depending on how far you are away from it. So if you're up in the sky, 5 kilometers above the Earth's surface, the D value in that Newton's law of gravitation formula is larger than if you're on the surface of the Earth. As a result, the force of attraction is going to be less, and as a result, you're going to experience less of an acceleration. Okay, we'll have a look at the textbook questions in a moment, but I want to go back and just check that we've covered everything from the success criteria. So here now is when you ask yourself, can you state Newton's law of gravitation? Can you use the formula? And can you calculate values? So if you want to state Newton's law of gravitation, if you gave that formula there and gave all the notation associated with it, that would be enough for a definition. Okay, can you give the relationship between F and D? It's a yes or a no. If not, then you need to rewatch the videos, and the same goes for between the force and the masses. And then, can you explain how it applies on a planetary and a human scale? We've done a calculation for each, and we see that the forces are substantial when the masses are huge. So when we're talking planets, the masses are huge, so the force of attraction is going to be quite big. But on a human scale, that's not quite the case. And the reason for that is because the G value there is tiny. So because the G value is so small, the force of attraction between two people is quite small. But when the masses are very, very large, as in the case of two planets, that small value there is offset by the massive values for the planets, meaning we get a substantial force. Okay, that's the end of video 2.